Hello and welcome back. Okay, in the last I/O video, I interfaced an RTC chip over SPI, and we did that by bit banging. Now, in talking about that, I did briefly touch on the fact that there's these 4 different modes of SPI based on all the permutations of the clock polarity and the clock phase. And the RTC chip we used supported 2 out of the 4 possibilities, specifically just one of the phase configurations. So what I'd like to do today is look at a chip that supports the opposite phase configuration, just so we can experiment with that and make sure that we know exactly what we're doing before I go on and build a circuit which we might accidentally put a limitation into. So I went looking for parts that would do that, hopefully one that was going to be useful to us as well. So let me show you what I found. Okay, so here's the chip I've been looking at. It's the MCP23S08, and this is an I/O expander. Effectively, it provides a SPI interface to 8 GPIO lines. And that's an interesting piece of functionality because in implementing the serial peripheral interface using what I was previously calling my GPIO lines, I've effectively used them up. So this is a chip which we can add to the system if we've got pre-existing SPI support, and that gives us GPIO lines back. My primary interest here is that this chip supports the opposite clock phase, and so it gives us a broader test base for looking at the future SPI circuitry. So it's an 18-pin device, 8 I/O lines. There's a I2C1 and an SPI version. We're looking at the SPI one. So you've got the 8 lines. You've got these address lines, which actually allow you to have up to 4 devices cohabiting in the system without using any additional resources. There's a reset, which puts everything back to default, so I could actually wire that up to my system reset line. That might be handy. There's some interrupt support, but that's not something relevant to us at the moment. And what I'm interested in here is that it supports mode 0, which is the same mode as a more complex device that I'm interested in looking at in a future video. Now, just like the RTC chip, there's a number of registers we can read or write from. Only a couple of those are going to be of particular interest to us at the moment, but might be worth looking at some of these additional features it has at some point. Now, the RTC chip had a 2-byte basic operation where you would send the address and then you were either writing the register data or reading the register data. But in this case, there's a 3-byte operation. So you've got the write command or the read command, an extra byte for the address, of which only 2 bits are relevant, and then you have the data. So it's a slightly different protocol, but there's a lot of similarity to what we've seen on the RTC chip. I think we've got the basic information we need now. Right, so I've got a couple of these chips. Let's poke them into a breadboard and see if we can get them to work. Okay, well, let's power this on and take a look at what we've currently got. So this is the basic GPIO board I created, and then we've got the RTC chip that I've wired into it with just enough lines to bit bang the interface. So let's give that a quick run. So that says 853. Now it's currently on my PC showing 850. So the clock's definitely running slightly fast. It's gradually gaining a few seconds. I should probably set it exact and track it for a little while just to confirm. But I'm more interested in doing that after I've replaced the crystal, put it onto a PCB so everything's directly connected. There's no issues about the battery source, etc. But it'll be interesting to see just how accurate these chips are. Now here's that MCP chip. It's quite a small DIP package. I am going to wire the outputs to some LEDs though. I've got some recycled wires from a previous circuit. So the lowest GPIO pin is that far one. That's a little bit tight, but that's going to be okay. Usual power and grounding. So interrupt line, that's not relevant to us. Chip select. Now that needs to be a unique line, so I'm going to put that into the next spare bit down. So that's bit 5 on the output. And we've got a reset line. Now, I don't want to run an extra wire from over here just now, so I'm just going to pull that high as it's active low. Should experiment with its use from the system reset line as well though. Then we've got the 2 address lines. Now, if we have more than one of these chips, that lets us chain them up sharing the same chip select. But for now, what I want to do is just pull them to ground so that it's on address 0. Then we've got SO, SI and SCK. Now, to avoid the arguments in the comment section of the last video, the datasheet clearly labels SO as serial out, but we just wire that to exactly the same line as we do the output from this chip. For serial in, we're going to do the same. Can't quite reach it over there, so I think I will just wire that in daisy chain off that connection. And then for the clock, will that reach? Yeah, just about. And of course, here's the beauty of SPI. We only need an extra chip select line per device we're going to add. Must be an easier way of making connections like this. When I put them with slightly raised ends, they do pack together a little better. Okay, well, I guess I need to try and drive this. Now, because each of these 8 lines are configurable as input or output, I think the first thing to do would be to test them as input, as that's the default. Use my trusty bus tester here. So, setting the switches with the lower 4 bits low and the upper 4 bits high. Now you can see that on the output bus there. I think it's going to be very difficult to do this without occluding those output lines. So now we see them on the LED over here. So you can confirm these wires work. So this circuit's just operating as a set of dip switches that are outputting onto this wire. Right, let's look at the code. So I've got all of my previous SPI code in this include file. Let's make our lives easier by defining some additional definitions. Now this chip is called the MCP23S08. And we put that into the 5th line. Right, so I've defined all of the register constants here. That's going to make life an awful lot easier for writing the code. Let's assume we've got a function called SPI MCP write. Actually, no, we were going to do a read first. I believe we get the current status of those inputs just by reading the GPIO register. So we're going to have a function that reads the data from there. And whilst we know we have to change it, it's pretty obvious that I should just start with a copy of the RTC version. So we're going to need to use the MCP chip select. And of course the protocol itself is slightly different. Right, so we need to write 2 bytes out. Right, this is what we need. So control byte, so it's got the slave address. The least significant bit determines if it's a read or write. And that bit is set. It's bit 6, so the write's just that alone, and the read is that ORed with 1. Take a note of that, even though we're not using it for the time being. So the first thing we want to do is write out that command byte. Now the code we've got there is outputting the data in D. We need to save that address off. So outputting the command byte. Once we've done that, actually saving the address. Then we read a byte in and return it. And that would work, I think, apart from the fact that that's in mode 1 and we want mode 0. Right, so we still need to get bits one at a time. But when we set the clock, we need the data to already be there. So we need to output the data, set the clock, output that, and then we clear the clock, loop back around to the start. That feels too easy. Do need to make exactly the same change here. Okay, maybe I should have done the write first. Read's a bit more complex. All right, we've got to reorder these as well. Now, the bit read, we're out of phase with the output because we're trying to sample the data midway between the data being set and taken away. I think this optimization is going to be a pain. I think that's right. Let's get rid of all of this. I'm just going to call this once for now, not loop it. Right, let's give that a go. Right, so we're expecting this to output F0, and it didn't. And I need a new line on that as well, of course. Okay, let's set the bottom 2 bits. Right, so 1 bit changed. So I'm guessing if I clear the 5th bit, I'm going to get the F0. Interesting, so the bottom bits are relevant. Everything's off by 1. Let's try that. Okay, E1's correct for how we set that. And that should be F0. Nice. Okay, that's working. I need to think through the timing of this slightly more. Okay, I get it. So we are supposed to sample here in the middle, but the first bit of the output is going to be available there. This is why opposite phase is actually a little bit more complicated. So I'm going to do that 7 times. And then the 8th outside the loop. Ah, no, right, this is not what I thought. So in this loop, that has the clock low. And then that has clock high. So when I say clearing the clock here, I'm just clearing the bit so that when it loops round again, it's cleared at that point, just because the way I modified the original code. So on the output port, let's get rid of that. The clock is set. So that's ready for the first bit of data to be read in. Then we repeat that 7 times more. All right, so that's still not right. Bottom bits are relevant, and the next bits are relevant. Have I gone the wrong way? Okay, I've gone the wrong way on this. The clock line is high. I don't need to read there. The first version was acting like it was reading in 1 bit too little. And the reason for that was very simple. The clock's high there, and then the clock's high here. So we've not changed the clock at all. We've just skipped a cycle. So that clock clearing operation we need to actually output. Then here when we set it, the new bit should be brought in for us to grab. Okay, that's correct for what we've got on the dip switches. As is that. Let's try swapping these all around. Awesome. Now I'm confident that that's working correctly. I was just slightly worried that first time we got it working because I could see I hadn't changed the phase I was reading the bit in. And what we were doing is we were reading the bit immediately before it changed. And whilst that would work most of the time, it's not something you want to rely on. Right, so that's input. Now let's think about output. So we want to write. I'm going to duplicate this. Doesn't need to return. We'll pass the data in B. Command byte needs to be right. And this is going to be far easier actually. So that code writes the command byte. Then we pop the address into D, write that out. I don't think it's necessary, but I think it's probably good to bring the clock low before we switch everything back. So we save the data. Need to fix the push and pop order in the SPI RTC version as well. Not a big deal right now. Okay, so MCP write, that feels really simple, as it should be, because we've already had the code to write 2 bytes and we're just writing 3 bytes. So that's the command byte, then the address, then the data. So D has the command byte, then we pop the address, then we pop the data. That's good. We need to write the correct stuff though. Now we want to make these lines outputs. So we set the bits in the I/O direction. And then we set the output latches to make the output. Let's go F0. Right, so we're going to be changing the direction of those lines, so we don't want to be pushing that value onto there anymore. Now the lines are currently configured for inputs, the LEDs aren't going to do anything. But the moment we set them to output, whatever's in the output latches will come out, and then we set in the code the output latches to F0. So let's see if this works. Nope, it didn't. One is input, 0 is output. So these default high, but I need to make them low to make them outputs. That's easy enough. That worked. Okay, so my code was correct for the SPI operation, but I hadn't quite read the documentation enough to know exactly what values I need to set to the registers. But we've got input and we've got output working there. I'm more interested in the protocol stuff, so I don't think I need to mess around with any more versions of this. Feels like that's working. I do want to move this battery though. So that's ground and that's power. And I want some more circuit space. So now before I go, let's see if we can test if this is all cohabiting nicely. So that will read the BCD seconds in to A, move that into B, and then we write it to the output latches. Initializing the direction we just have to do at the start. So this is 2 separate SPI devices now. We're reading the seconds in, writing to the output latches. Re-enable the loop code. This should be fun. Okay, I see something changing there, but I think I pulled one of the wires out slightly. That seems to be counting up seconds. That looked like it jumped there, but that's actually, this is BCD, so when the bottom 4 bits gets to 10, it's incrementing the top 4 bits. That's kind of cool. So we've got the RTC chip counting seconds, then the GPIO, then the MCP output chip is lighting the LEDs, and then all of this stuff, the CPU, is just connecting the dots between them. I think it's a nice little demonstration that it's working there. Okay, I think I did quite well there. I'm never going to get all the coding right first time, but we did get the circuit working. So now we have 2 different SPI devices operating in 2 different modes that we've got consistently working in the system. And that gives us a good foundation to move forwards. The next thing I'm going to do to this circuit, I think, is start to add some additional support circuitry to the SPI, because those chunks of code are very repetitive and we spend quite a lot of time kind of setting and resetting bits in the whole bit banging procedure. Really happy with it though. As always, I want to extend a big thanks to all my patrons and everyone who supports me in any way. I very much appreciate it. I hope you all found this interesting. Thanks a lot for watching, and I will see you again soon. Goodbye.